talk which contains some tutorial material and understanding both the theory, science, physics, and then present the same concept. So I start by studying about the factor of global energy, and then all the quantum geometry and superconductivity. Then mostly whether it has something to do with physics, and then I have review results, but not even in the archive yet. And then the first part is about intelligence, superpowers, so then I go to language reasoning. And finally, the last two topics are not about superconductivity. They are away from other topics, but just an overview of quantum geometry that really appears in many places. So let's start with this factor of superpower, and it's related to superconductivity, which you know is extremely useful in the large levels and sensors and maybe in field reactions and so on. And this here is a factor of 2. So why are we still at 150 and not at 300? Because obviously all these applications would be much more dramatically important if you could get there. But still, after decades and decades of the century, we are still at 100. So let's have a look at what might be behind this main factor of 2. Well, this is the same relation carried result of critical temperature. It's inversely proportional to the interaction scale U and principal state. And you understand that when there is something exponential in the game, then of course also something to index factors. So basically, if you want to get this TCA, there are two things we could do. We could increase the interaction factor, increase the density state. So let's think about this density of state stuff. So if we make the density of state infinite, or in other words, if we kill the kinetic energy of the band, then the interaction is exponential. So this is what is going to be positive. And in these people, you may look at that. And here you see also in this tutorial, it is very easy things. This is a single band in the periodic part of the block part. So here you see this will be very important in my case, but you know this in my process. Now we can run the so-called flat continuum, where I think this is completely flat, so no displacement, no group velocity, or it's approximately flat. Then the interaction scale is bigger than the band, if you can call it that. And now, it has been shown, we won't be able to look at although it was given later, was more showing this thing, that actually the critical temperature to superconductivity is such a factor. It's linearly proportional to the interaction energy and the volume instead of the exponential calculation. And this for this interaction is really like an exponential decrease. So this looks very good. So this is only the theory temperature actually. So the closure is absolute value that absolute value of the order parameter could be enhanced in this like that. But our order parameter is small. No. It's this kind of open. Very open. And the reason of a superconductor is just to have a supercurrent or larger effect. And supercurrent is very different from the neutral current, which is proportional to electric field, this is proportional to the vector potential, and according to the growth of superfluid rate or superfluid stiffness, which is less. So that has to be non-zero, according to another superconductor. And we might not one, but or the parameter is not based in the value of the phase there. However, the derivative of the phase minus the superconductor is phase volume. So actually, you also need to isolate the point what the physical meaning of this thing is. If you put something current in your system, so from here is the phase, and you calculate how much you see, and the phase is given by this data. So that's like, in other words, like the inverse effective mass of the numbers. So you put it as volume, what is their mass? So it's a really key important, and it also is inverse of the penetration. So when we have this inheritance, so let's look at the formula in conventional ECS theory. The superfluid rate is proportional to the number of interfaces divided by effective mass. When something is and then you see the problem. This is actually zero as well. So it seems in my thinking that this could mean that the superconductor network would be as much important if maybe not that there would not be any superconductor. But this is like a result for a single time. Now something else happens in the multiple system. Actually, all the lifetimes that we use are still interesting. They are multiple systems. The flatness of the band is from interference. If you could have also flatband as a trivial flatband function and localizing the electrons really tightly at the considered basis of this. But that's interesting something. However, we are case like the lead lattice geometry here, now you can see that there can exist static space where the amplitude of the radiation is plus from here and minus from here. And now you think about tunneling to this side, obviously there is destructive interference. So this kind of destructive interference forms particular state at the other side. And that leads to the so this kind of flatband exists. And another way of thinking how you can create a flatband is that you have a bar structure. Lattice then with a super lattice and to follow the minimum flows and of course think it a bit faster. This is how we exactly example of this thing. These two things are actually the same thing but one in principle and one in the real space. So it's all about interference to create a flatband. So in this kind of system now, we can actually have that I will say is one is flat and everything will hold. And we started to work on this in 2015 in my group and I want to highlight how very important to work with and study to the various phases of this work and I have also quite collaborated with Uber and lately undergraduate has been very cooperate. So this is kind of so I emphasize that we have to look at some multiple programs. So let's do something in one way about the multiple. So we can plan and they have that model use of that model and try for actions exactly once. But now there are just one topic and in this case we take to the correct orbit. We have many orbitals. We live in the past. How do you calculate this important distribution rate? You can get it from between everything you get in a supercarbon with a multiply. And let's say how much your energy. Also, using this relation between the order parameter phase and the vector phase, so it gives you understand that, okay, we can get the same result from linear response, the rate is the linear response to the vector potential. Like I said, it always says it's going to take. And in third realization, we can see that it's actually the cross potential. And this is the result. And this was what we want. So we found out that the superconductivity makes us two contributions. One is the one that people have always appreciated already. It's proportional to the derivative of the expression. In other words, the inverse effective mass, and that would be zero. However, there is another contribution that only appears when you have a multiple system, and this is present also, it's non-zero also in a factor, so this is good news. And we call it correlated. Well, what is that? Here I have to go on into this quantum geometry. Many of you already know, but maybe some don't. So let's go to the very basics, and these people are interested in defining a gauge invariant matrix for the distances between quantum states. So obviously here I have a distance between two quantum states. You parameterize by something and you change the parameter width between the distance. This could be both functions, this could be the lattice momentum, this is also something good. Now looking at this, we actually found a more general object of quantum geometric data, which has the derivatives of the wave functions and so on, and it's clear about this metric for distances between quantum states, and really the metric without it of distance. And the imaginary part tells more about the first distance, meaning the derivatives. That is, of course, relates to the topology there. So, other than to then study mathematicians have known this for 100 years. And they implement it. And I think this people thought that it might be useful in general context. And what talking about relative is the general extremely well known already. This quantum logic is only emerging now in quantum context. So, in the tutorial stage, I also like to always to take the simplest possible system and try to understand it. So, think that your Hilbert space is the common system. Just to take two states, 1 and 0. And this Hilbert space is a manifold you can parameterize completely by two electrons. It's a block sphere. Okay? And then you can use this formula to do it very quickly in the back of the envelope. You can still have it here. The quantum metric for the sine angle is sin squared theta. And you understand, if you are at a north pole, it's just a zero state. And now if you change the sine angle here, and then you look at what is the distance from that initial state to that state, it's of course zero distance, because any product is still overall phase doesn't matter. So here, indeed, the quantum metric is zero. Now at the equator, so the superposition of 0 and 1, and there, if I change the angle phi, it matters. You can even by changing phi, you can make the state orthogonal to the Earth line. So those have a big distance metric. So it's good. So it's working out with this kind of convenient way of telling how much your state changes when you place a parameter at different points of your parameter space. The parameter space could be also found. So now that you understand that when you tell me, when I say that we have shown that actually with some limits, this geometry part is proportional to the interaction of the quantum metric. So the quantum metric is there. It's superconductivity. And it's here very high. guarantees superconductivity in the field. So let's look how did I come up with this, come up with this mental matrix. So this actually can be derived in a limit where we think that the platform is isolated. So the boundary is supposed to have to be smaller than interactions so that it's a platform, but when the interactions is smaller than the platform, then we can call it isolated platform. And moreover, I assume that the pairing is the same of all orbitals, the exponential. And this actually happens when the orbitals are related isomorphic. So that's something to listen. And that limit, there is a very beautiful formula to how the superconductivity looks. So it's linearly proportional to interaction. In the same way as the test in the platform. And the name is C, so it's a creative transferring, it's not the orbitals, and this thing is now the quantum metric integrated over the regular form, and you have to take the minimum value of that. So this has been derived both by mean field and also by exact calculations. Here. Yeah. So we can also write both delta, and in the platform it's like this, just interaction. And then you can relate that the is the proportional to the square of that. So very different from the Bose-Einstein result which was significant at the first divided by that is not even by the other time. So first about this quantum metric, very famously, some well-known concept that I didn't even, I think even the reading articles have not fit to this time. So I didn't mention something I can't do. Aalto in 2009, I was able to list on one slide all the papers that I read about this quantum metric. And after that, the research has really exploded. Of course, partly because I was listed for the superconductivity council before with the now, this quantum theoretical tensor is actually a positive superconductivity tensor. And this allows to divide unit to superconductivity in a flat path. So it's always possible, definitely, if there is very curved somewhere in the flat path, or the lower limit is actually not experiencing speed programming, because there might be very much of the systems. So, topology helps in that. So now, I started by working with the factor of 2 and level 2 in picture with the change, with the lectures that it is place, but now the list is understanding that there is a curve in gradient. It's the quantum theory of the topological picture also from superconductivity. So we have to understand the properties of the platform. Good. Okay, maybe let me now go for the familiarities, want to get some intuition, and I also wanted to get some intuition after the initial results. So I talked about trying to do the Cooper program. You remember, it's a theoretical work by Cooper where he has solved the Cooper scattering problem, but assuming that scattering is limited by the frequency. And from the simple calculation, he got complemented of this form, which is the same as you get from manifold in previously. So, to try to do that, in example, of course, you can write down the two-particle Schrödinger equation, but we have immediately a problem with no condensation. In flat point, okay, flat, maybe we can say there is no such concept. There is no flat substitute together. So each person is actually completely different. In that like any interaction in fact is the interactions where pictures how it's distributed, but you can't all because where we have on the frame, very big part of the process. And the flow is the momentum of the flow. So in here, actually, when you have the fluctuations, which is very uniform, you can then take the full kinetics, which will give you the effective mass, and that turns out to be proportional to the quantity. So you get also here, like the original group of problem, you get the same result as the simulation scheme manipulation gives you get it two quantity. And maybe this helps also somehow to understand that, okay, the pair can be explosive in the maximum application. Yes, and a bit more of this intuition study. Now, let's think about this two different types of platforms. Here I have trading platform where you just really lightly optimize electrons. Because here is the other one where you can use interference, and there I actually don't necessarily need to have very nucleus electrons. The value functions can be quite right. And now if you have interactions in this trivial compound electrons external colors, but in the non-trivial one, with interactions to get movement. And this overlap, of course, then a filter that I can get something like supersonic expands over a whole system. Now, this is another angle of the collection of quantum geometry. Namely, it is well known that the localization properties of quantum functions are connected the quantum geometry. And for instance, if you have a function time level, you can also exponential localize. But basically, the quantum metric guarantees that your memory functions are sufficiently localized so that you can get so what I showed so far was this Mayfield and Philippe results that there is much numerical work maybe or dimension here at the front. And Mayfield works with so basically the same methods. One can do also a favorable theory that's projective as a small group. And this is in this work. The part one is if you leave an isolate the paper and you project in the maximum area, there it becomes a space form. So basically just stick densities in square, so it's positive symmetry. So this actually allows except results. And here these results anti-dynamics group. And we use this projector. Let's say that the projector means so this is a projector to filter to have more than one if you wish. And we have this uniform theory, this expressed with the projector looks like this. There is some reflection or the junction. This sounds. Now I can show that this Hamiltonian, the predicted one, has an exact ground state of 8 pairs. So this one of pairs, which is superpositions of many. So it looks just like people data or any data. And this Hamiltonian has explications. The point of direction is bound by a single particle Hamiltonian. So this kind of this is just a contained projector. So this you can solve exactly. And from there, now, I get the same result. I will show already from Mayfield or from the two-part problem. And the effective movement effective mass is the best way to read. It's the best way to interactions and this minimum effective connection. So it has been shown by quite many companies. And then they represent all kind of other modes or something like that, for example. Now, I spoke quite many times about this alternating transfer, but that's just because theory is related. And it's easy to calculate, but of course, in real materials, actually defines the first even some kind of ideal condition. Because one can do these things numerically, and then you see that actually it's often better to have some kind of absolute like that. And this is the reason that it's where you never do that for something. Yes, but you can look at that directly. Here we vary the graph is that. This is the business temperature, the critical temperature. You see that it's the best that so that's interesting. But the figure is to have a more amount of temperature, so that's fantastic. This figure contains another important message. Maybe there is this what is this? Well, let's square out of the together you can see that for us interactions is very higher. So for us, typically, when the interactions is now quite small and the space is very important, small in open space, the air is really like exponentially better. So it's an enable likely to do some express when the interactions are small. Right. So I already mentioned that we start now with superconductivity and almost flat bands. So what I actually want to ask whether these things have some relevance of existing in practice, of course we don't need to introduce these things, I mentioned here that we have a regular optical level about this one. So, the organizations of this group are instead of whether this quantum contribution is there, activity, and then some other papers started to take some indicators like paper by the papers, the office, and they were correlated. And all of them kind of say that yes, it helps something. It says B, we don't know what it has. And so we calculate it, so we but again, the multiple now we try two types of tracking answers because it's small, really what kind of value to take. So the nearest neighbor is kind of RBG type and that's not small. It's very so. And then we calculate the superconductivity rate as a function of interaction here for the two types of interactions. And we speculate what is the usual contribution, because this flat bands are complex results, they have a little bit of dispersion. So you will have to highlight that we get some contribution to the superconductivity rate there. But there is also the thing of so the peak is the conventional and the geometric one. So depending on what your interaction is, they must be a considerable contribution. Now, the theories of DPT and have developed tremendous methods to theory, so I will not stress this quantitatively, but I think the question still is very valid to try to see what is the relation of quantum geometry in this system. And there is one experiment that they tried to prove that. So they didn't measure the superconductivity rate directly, but they measured the critical field and the critical power, and then used this kind of BCS relations to deduce the superconductivity rate from there. And as a function of feeling, it is this red curve. And here, is what the user is therefore to the time, not here, the effectiveness is of course completable. And then they have some other status between the and that, for which it takes a bit better. Then you will already result of the isolated pattern. So maybe this is a last thing that they can do something about this correlation. But this is a risk machine. So now I go to something new, and now also the people who have heard that go in there, like Andre and Rita, these are unified, so some of them are in archive, but I show something that is a new people. So, I have shown these large analytical results that you get when the blood view is isolated, and we have all kinds of other correlations also, sometimes simultaneous in the comparing. All this really is useful and valid if we take other types of points and also compare with the ways. So here we try to explore that by looking at different types of link lattice geometries and doing dynamic matrix theory with close field medium treats for the local cluster, etc. of the rest of the So, there is a very beautiful work by Andre Wilhelm Spock which shows that if you have hypertype lattices with a larger and smaller sublattice, they will always have this amount of flat paths. And the local states are only on the outer subtype. So, for instance, in the list lattice, the smaller synchrotron is A, and the larger one is 6. So, 2 minus 1 means there is 1 flat path. You can have more complicated lattices and more flat paths. And here I have the result that we have shown similar times, as you will calculate. And then I have added actually in some of these later work, this is essentially from this one, but in the later work we added that proportion of the number of flat paths divided by number of orbitals make a flat path. So this is something we want to test now numerically. We took some modified versions of these matrices, like original one of them, corrected, extended, twice extended, putting something here, and now there's a different number of orbitals and flat paths. So you can really change this on a flat path of limited value. So let's see what happens. I mean, you can calculate what you get in the CMSD method by just taking back the difference from inland from the current formula. But here you see what happens. So in this, we get the best critical temperature ranges and flat path areas here is the best. So it's the best one. So then we wanted to study more of this type of extended lattices, and you can extend now in many ways. You can have other ways of things like this, or ways of this, with different numbers, demand structures, things like that. And here I have just had some So, this is supposed to be a tutorial for my lectures, for the lecture of my university thesis. So now I would like you to think, but yes, this of course successful in a best superconductor. Until you will make wrong. Okay, so here we go. And I will see how. Okay, now you have your favorite and don't vote because you see somebody else who is just for you. So don't vote for this one. what do you think about this? Is it this? Is it this or this thing? This one? This? And this? Yeah. Okay. So, I will not call it what is that because there is one more exercise. So this is just a box structure. And then let me show the example exercise. So let's go up all the time. We know it's to produce one now again, right? So who wants to this? This one? This? And this? No? Okay? And finally, this is the last one. So here we take this one, this, and this. Okay. Good. So some of the backside will look very similar, but of course this one will look like that. And now I have here, so here actually this one is the base, and here is this one. So you can see how these different ones depending on the basket opening. And it's really there's a number of lifetimes to help. Of course, so these are always better. But it's a very valuable thing about the quantum mechanics. So here it's very strong here. But here for instance, we have the distance to it. And now it's really they have just along the high symmetry axis, but if I'm placing it in two dimensions, it's easy to see that, for instance, this one has large quantum density in many places of the radar field. So this is a bit of something that we realize here, that it might be interesting if you look at cloud banks where there are other almost flat banks nearby. So even when we're doing a lot of work on we have always stopped in the cloud bank because we have structures to violate roughly. So for instance, I will get you assistance to every time you're given for that. But I think this kind of thing is something to look at. There is also another point here. That this interaction is very small compared to the scale that is separated by two, and the interaction is like this. So, because it's the quantum geometry, I understand that people might look at the band structure of some real materials and say, okay, here is one band, it's pretty isolated, and the interactions can be small, so let's make see what that one thing of your hammer or something. But if the band is contract, if the quantum metric is not, it's completely wrong. Because for the single band model, you don't get the quantum metric unless you don't have the current direction of the field. So we might have to do this things to see how many bands you actually have to take into account. I mean, it really depends on the quantum metric. So it's necessary on the interesting scale. So then, okay, let's have a look. What is different methods to see the products of the different results and things like that? The scale. The two-to-six values of the superconductivity. So scale represents the cell temperature, specific weight, and the preceding weight of the cell. And all of the matrices that fall in the same line is 1 minus t is 5. And well, this comes then from the I think it's I'm having the results that are coming from because we also see that the other part of the space. And this then is very difficult from using this result, which is first 1 minus still 1 minus 0. So it's not it's not sense that space is not bounded. So this seems to be true in this moment, but what surprised to me was that we could isolate this flat from single temperature and so on the side. Which seems to be actually really nice. So I don't know where this follows my and how you remember something just how this looks. Right. So let me go to this few other topics briefly. So because I think it's funny. So superconductivity is our supporting factor, it's actually a constant topic, but they could also have a molecular signals and using voltage. So this started this way, and again, a bad model, multiple measurements included in the form, so it's the index number in the form, and we show now what was our neural system, the system. So this kind of modality has flat points, like this. Of course, a finite system doesn't have that, but it has states that are like that, and they are mobilized, and they are this kind of state. And then we can leave and be superconductive. And we can also have like weight, but also we can explore the flat point for the space. And then we calculate the power. And we can, since we have all the data, we can pick up AC and AC component from AC here, that in this space, everything goes through DC, AC, non-independent, but in that way, it's only the AC in the interacting case. So this is the superpower. Nothing else goes through. Not even the AC current in the interacting case where we have a spark conductor there. And that's a big challenge because AC current is in a flight voltage comes from underlying factors and sorry. So basically and this is a coherent process, but it does involve multiple underlying factors, which is supported by the group. It's a passive particle process, so it seems that this is suppressed. This is a usual chemical process, or different systems of this structure. But here it seems not to exist. And that we have lower limit, nothing to do with that. So it seems based on this molecular study that that actually could have a pure superpower, no possible transfer, not even the multiple molecular effects. So this is what we have for the magic. So it's not only the critical temperature that we speak about, but also chemical temperature. It's possible. Yeah. So then I think to completely different topics, and you might think of what happens to Bose-Einstein bodies in a unit of atomic particles. And this is interacting, so we usually carry such a calculate to sort of quantum deflation from how many particles are in each hydrogen state just because of interaction. This is it's still not plus. And then if you have effective intermix on these diagrams, so you will probably have excitation on the space. This is my technique. But even there, actually, we found moments, if you take into account the axis, you can find a minimum, and then what is the same is stabilizing completely. And we found that actually the speed of field is proportional to the square of the particle matrix. So quantum geometry comes out from there. Moreover, we show that this quantum deflation is based on number of excitations in the states. This depends on the quantum distance, not metric number of quantum we will have, when we decrease the total density, we will have more and more expansive state occupied, meaning that you have more and more quantum fluctuations. So flat bands is the way of bringing your condensate beyond mean. I think, if you have done a study about molecular quantimetric as well, which is a particularly much more predictive as well. The final output from the actual problem is a problem. And here I put this as the last, this is the last slide. If you got interested in this topic, I can print this out because this is really my concentration. On Friday evening, this is the 10th of May, and within